in 15.1, we talked about double integral already. At that time, do you guys remember we had that double integral over what kind of region? So at that time, the region that we have, it was a rectangle. But today, we're going to have double integral, not just over a rectangle, it is going to over a general region. Okay, so this kind of region. Okay, so that is called the general region. Now, how do we do this? Now, remember last time we talked about double integral geometrically. If the function here is a positive function, we can interpret that as the value, right? Single integral corresponds to the area under the curve. Double integral here, if it's a positive function, think about that as the value under the surface, right? Okay, so the value under this surface over here of this big F is the same as the value under the surface of small f, because outside of that it's going to be 0. 0 here and 0 here, okay, inside the rectangle. You see the blue region over here, down here, has no value, okay? The function value will be 0. All right, so any question here so far?
From this figure, we see that on this rectangle, the big F function has function value to be 0 on the blue region. And then all of a sudden, it jumped to the function value of small f on the orange region. So it is likely that the big F function has discontinuity on the boundary points of D. However, if the small f function is continued on this orange region D, and the boundary curve of D is well behaved, then we can show that the double integral of the big F function over this blue rectangle exists, and therefore the double integral of the small f function over this orange region D will exist. And in particular, this will be true for the two types of region that we're going to talk about later.
This is the first type 1 region. This is the type 1 region. As you can see here, the x value is going to be bounded below by a constant, bounded above by a constant b, right? So x is between a and b. So x is between two constants, a and b. And then the y over here, so you have two curves. This region is, you have one curve here above, one below. One above, one below. One above, one below. Then this kind of region is called type 1 region. What do you think about type 2 region? What kind of region you can imagine? A type 2 region, let me give you an example. This type 2 region. Okay, you see that the region here is bounded on the left by a curve, bounded on the right by the curve. X is expressed as a function of y, x is expressed as a function of y, and then the y go from C to D. Y go from C to D. So these two are type 2 region. So keep these two type of region here in mind. Okay, let's go back to the type 1 region, where the region here is bounded above and below by two curves, where y are function of x, expressed as function of x. X go from A to B. We are going to choose a rectangle. So you're going to think about a rectangle that is going to enclose this region. Okay, so bigger. Okay, and then we're going to we do the same trick, right? We're going to let the big F function equal to the small f function over this region. But outside this region, but inside the rectangle, you're going to make the big F function value to be 0. Okay. Then the big F function is going to agree with the small f function on this region. And the big F function double integral over the rectangle. Okay, so that is the R. This is the R to talk about. And then this D over here is this region over here, D. Then this double integral of the big F function over this rectangular region is equal to the double integral of the small f function over this orange region D. These two are equal. Because outside this orange region, the big F function value will be 0. So these two will be equal, okay? But we know how to do double integral over a rectangle, right? Like 15.1. And what do you do? We integrate either with respect to x first or y first. Okay, it doesn't matter. The result will be the same. It's equal to this double integral. Okay, y go from c to d, and x here go from a to b. Okay. Actually, they might have a better picture over here. Okay, see they have the picture here. So y go from c to d. Okay, and then x here go from a to b. Okay, so we integrate the big F function over this blue rectangle here. All right, now what happened to the blue region here? Outside this orange region, in this blue region, what is the function value of the big F? Do you guys remember? It's equal to what? The function value is going to be equal to 0, right? It's equal to 0 outside. And then in this region D, the big F function is equal to the small f function. So that's how we define the big F function, right? So in this region, this function, big F and small f agree, but then outside that region, we make the big F function, the function value to be 0. So because this blue region here, the big F function value is going to be 0, okay? Therefore, so if it's below this curve, then what happened here is the function value for big F will be 0. So it's not going to contribute to the double integral because function value is 0. And also, if it's above this curve, right, above this curve, the function value for the big F is also going to be 0. So it's not going to contribute to the double integral. So what really contributes to that double integral here is when the y is between this curve and this curve. When y is between g1x and g2x. Remember when we do double integral, we do the inner integral first, right? So let's focus on this inner integral over here. That double integral here is integrating with respect to y first, right? And y go from c to d. And because the big F function equal to 0 below this and also above this, then the only part that contribute to this integral here is those y that is going to be between this curve and this curve. In other words, y is going to be between g1 of x and g2 of x. Only this part, right? So when y is between this and this, then the big F function value will not be 0, right? Okay, it will not necessarily be 0. Okay, so these two are equal. Okay, now what happened to this between this one and this one? Between this one and this one, when y is between this one and this one, the big F function is equal to the small f function. They agree. That's how we define the big F function. So we can replace this big F over here. Can we replace this big F over here as the small f, because big F is equal to small f on that region, right? On the region D. So now we can replace this by this. So that is equal to this integral of the small f function integrated with respect to y. Y go from g1x to g2x. Okay, and that's what this integral here, right here, the inner integral here is going to be this. So keep this in mind. Okay, I'm going to actually box this so that you see this is equal to this, and that's equal to this, right? Now, can we put this back? Can we put this back into this double integral? If we put this back into this double integral, what do you think we're going to get? Okay, let's put it together. So we're going to get this double integral from a to b. Now, and then here is x go from a to b. And then for the inner integral, what do we put over here? We're going to put this one over here, right? So I'm going to copy this. Okay, I'm going to put this one over here. So after all this explanation, we know that when we try to do the double integral of this small f function over this region D, that's equal to this double integral over here. With the inner integral over here, we would integrate with respect to y, but y go from g1x to g2x, and then x over here go from a to b. Do you guys got this part? Does it make sense? If it's the type 1 region, remember type 1 is like this, right? It's like this one, okay? It's bounded above, bounded below by this two curve, and then x go from a to b. Then you will have integrate with respect to y first, and then x later. X go from a to b. Okay, so x is bounded by the two constant, a to b. And then the y over here, the inner integral is integrate with respect to y, and you just need to think about the y here is bounded below by the g1x and bounded above by the g2x. So you have two curves. One, this is g1x, and then the other one here, this is g2x. Okay, and here this is a, this is b. When you have a region like this, then you're going to integrate with respect to x later, but integrate with respect to y first. Okay, y go from g1x to g2x. Okay, so that was for type 1. Similarly, what do you think about for type 2? So suppose you have a region like this. This is type 2 region. The y here is bounded by the two constant. The two constant here is c and d. Okay, and then you have this region over here. The bounded on the left by this curve, bounded on the right by this curve. Let's try to think about what will be that double integral. Okay, so the double integral of the function and over this region D, that's equal to what? Okay, let's try to write this together. Okay, so integrate with respect to what first, with respect to what later? Can you guys think about it? With respect to what later? X first and then y later, right? So you have y later, y here, right? And then x first. Okay. Okay. Y here go from what to what? C to D. Okay, so y go from C to D. This constant to this constant. Okay. And then the function over here is pseudo-sum function. X here go from what to what? H1y to H2y. You got it. Good job. Okay. So H1y and then H2y. So the idea is kind of simple, right? Now it's not that terrible, right? Okay. But after all the explanation, right? Okay. So this is for type 2. For type 2, you do this. Okay. So when y change from a constant to another constant, okay, like that. Any question here so far? Now let's try some example. Let's try to evaluate this function over region D, and that region is bounded by this parabola and this parabola. Okay, so maybe we should draw the graph first. Okay, you're able to see that this is a region. So bounded above by this parabola, bounded below by this parabola. Is this a type 1 or type 2 region? Someone say type 1, someone say type 2. Okay, 1 or 2? 1, okay, that's 1. It is a type 1 region because it is what? It is bounded below, right? And then bounded above, like that, okay? So this is the type 1 region, right? Now, if it's a type 1 region, then we can set up the integral for this, set up this double integral, right? And how do we do this? Now, without looking at the book, let's do this together, okay? Okay. Try it, okay? So when you have this double integral, this function over this region D, then that's equal to this double integral, and it's the same function, x plus 2y. Dx first or dy first? Dy first, yes. And then later on dx, right? Okay. So x go from what to what? X go from -1 to, looking at this region, right? X go from -1 to 1, right? So x here go from -1 to 1, okay? What about the y? Y go from what to what? From here to here, right? So it is actually helpful if you can draw this. Okay, once you identify the region, you can try to draw this segment, nice segment, label this with an arrow, okay? So y go from here to here. So y is going to go from 2x squared and then all the way to 1 plus x squared, right? Okay, so you just set up the integral, right? And I think that's the most crucial part to do, to set up the integral. Because after this, it's the same as what we have done in 15.1, right? Almost the same, right? Okay. So good, okay? You guys are able to set up the integral, okay, which is this one over here, okay? So this one over here. Now, how do we do this integral here? Okay, let's just try one time, okay? And this is as a review, okay? What's the antiderivative of x with respect to y? xy, okay? What's the antiderivative to y with respect to y? Y squared. Yes, you got it. Good job, okay? So you get xy plus y squared. After this, what do? We plug in the upper and lower limit, right? Here, y here is equal to y over here is from this to this. Then we can just substitute the y in. So plug the y in, and you do all this algebra calculation, okay? And then after that, you want to simplify it as far as possible. And then you find antiderivative this again, which is just a regular single integral. We know what to do by antiderivative, and then you will get the result. Okay, so I think the most important part here is you know how to set up this integral over here. Okay, to do this type of problem is actually it's going to be very helpful if you can graph the region. Okay, so over here we graph the region. Label the curve above and below, and you know that this is a type 1 region, and it is better that you draw the nice segment, and put an arrow like this. Then you know why here go from this to this. Okay, and then you can also see the x here go from -1 to 1. So this is the type 1 region. Question here so far? So the diagram actually will be helpful. All right, so let's do the second example. We're trying to find the volume of the solid that lie under this parabola and above this region in the xy plane, bounded by y equal to 2x, and then the parabola y equal to x squared. Okay, let's look at the Let's look at the graph right here. So basically, it's this region. It's this region. Bounded above by y equal to x, bounded below by y equal to x squared. What kind of region is this one? Type 1 or type 2?
It turns out that this region can be regarded as a type 1 region, but can also be regarded as a type 2 region. Let's regard this as a type 1 region and do the double integral first.
And once you draw the region, it's helpful that you put a nice segment like this and you indicate from lower to upper, right? From below to above, okay, like this.
And now we're trying to find the value of the solid that lies under the paraboloid z equal to x squared plus y squared, and then above the region D on the xy plane.
So imagine above this region, you have a paraboloid, okay, and that part, okay, and under that paraboloid, okay, under the umbrella, right, then you want to see what will be the value of it. If you want to see a picture, so maybe something like this, okay, so you try to find the value under it, okay, under the paraboloid and over the region, okay, so you try to find something like that. So we have a paraboloid. Imagine this parabola here is the surface of that above this region, okay? So imagine that it's a piece of cloud in the sky, okay? And then the shadow of that piece, okay, is this one. And we're trying to find the value of that right under that piece of the surface of the cloud above this region, okay? Imagine that, okay? Then how do we do that? Okay, let's don't look at the book and try to do it ourselves, okay? So the value of that, we know that is going to be the double integral of the function. What is the function? The function here is what? This is the function, right? Z equal to this. That's the function, right? Okay, so it is going to be x squared plus y squared, that function. And over the region, so it's a dA, like a small change in the area, over the region D, so put a D over here. Okay, so that's the integral that represents the value. Now let's do this. We have x squared plus y squared. Now we know that this is the type 1 region, so dx first or dy first? It's going to be dy first. I hear you. Okay. So it's going to be dy first and then dx later, right? Okay. Because you can see right here. Do you see right here? Is actually the y go from, see the y over here, right? You see the y? Y go from this to this. So you have to do the dy first, okay? Because y go from here to here, okay? So let's put that in. Y go from x squared to what? To x, right? Okay. And then x go from what to what? Yeah, the x here go from 0 to 2, right? You look at the region over here, right? So 0 to 2. So you're able to set up this double integral to represent the value of that under the surface of this paraboloid and then above this shadow. Okay, so that's the value. You imagine the piece, the cloud right there is going to rain. Okay, so the rain, what will be the value of those from this cloud to that shadow right here? Okay. Okay, so once you set this up, the rest here is just routine. We know how to find anti-duality. Okay, maybe just one more time. Okay, see if you guys know how to find anti-duality. Okay, let's do the inner integral here first. What's anti-duality x squared with respect to y? Because when you integrate with respect to y, we're going to hold the x here constant, right? So think about x squared as a constant. So anti-duality x squared with respect to y is what? X squared times y, right? Okay, good. So that's x squared times y. And then anti-duality y squared with respect to y is y cubed over 3. And then you just substitute y to be 2x, y to be x squared in it, and you just do the calculation and finish it, right? Okay. All right, question here so far? Okay. I think we might need more practice, okay, on the region. Here's the animation, okay? So, and you can see this, you should grab the two, you should grab them, okay? And you also label, you label this, okay? The y here go from this to this. Then you see this is the type 1 region. You can also do it this way, right? We can also do it this way. Then it's going to be left and right, right? Left and right like this. This is the left curve, this is the right curve. So now this is going to be a type 2 region. So that region can also be type 1 and type 2, okay? Depend how you look at it, okay? So we just did that using the type 1 region, but now let's try to use the type 2 region, okay? How about we try to set this up without looking at the answer over here. So that's the double integral. The value of that function, which is x squared plus y squared, okay? And integrate over the region D, that's equal to x squared plus y squared. Now, if I consider this as a type 2 region, we're going to integrate, you're looking at this, right? You look at this arrow, x go from here to here. So we integrate with respect to x first. Okay, so x go from what? 1/2 y to square root of y. So you know that it's always go from left to right, right? With this arrow here. And then after that, you're going to have a dy. Y go from what to what? 0 here to 4, right? So y here go from 0 to 4. Okay. Yeah. So if you consider this region here as a type 2 region, then you can set up the integral this way. And it turned out, if you do the calculation, the answer here will be the same. Okay. It doesn't matter. So sometimes the region can be a type 1 region and at the same time also be a type 2 region, and that's possible like this, right? Okay. So this is a type 1 and also type 2. But sometimes one of them might be a little bit easier. So sometimes this integral might be a little bit easier than the other integral, and you just pick the one that's easier to evaluate. Just pick the integral that's easier to evaluate. So if you have a choice, if it's both type 1 and type 2 region, then you can just pick the integral that will be simpler to evaluate. Okay. Question here so far? Okay. Okay, let's look at another example here. So they give you a double integral and the region is like this. Okay. Is this region here can be both type 1 and type 2? Which one is better? Actually, if you do it as a type 1 region, what happened over here is, do you see what happened over here? Okay, let me see. Actually, over here at this region, right? At this region, this is above, this is below, right? And then over here, this is above, this is below. Then you have to consider two different cases, okay? Like that. But then if you do this a type 2 region, on the left and on the right. This is on the left, this is on the right. Which one you think is going to be a little bit simpler when you set up the integral? This one, right? Looks like this one here is a little bit simpler, right? So this one here is, okay, type 2 region, because it's going to be 1 on the left, and then here we have 1 on the right. So it's a little bit easier, okay? This is the right, and then this is the left. So you probably want to pick this one, okay? It's a little bit simpler, okay? For this one here, you have to use this above, this below, this above, this below. You have to consider there's 2 cases and put them together, okay? Divide that. Okay, now, if you think about this as this type 2 region, like this, let's try to set up the integral without looking at the book. Okay, how do we set up the integral? What was the function that we integrate with? It's this one, right? Okay, let's set this up. Just look over here. Okay, I'm going to do it together with you. Okay. And I'm going to make it like this. Integral xy. Okay, integrate with respect to what first? Okay, take a look here. This is what? You see, you draw the arrow like this, right? Okay. So this is x change from this to this. So integrate with respect to what first? X first, yes. So dx, x go from what to what? Left to right, right? So this is 1/2 y squared minus 3, and then all the way to what? Y plus 1, okay? And then later, and then we have this dy. Y go from what to what? -2 to 4, okay? So -2 to 4. You just set up the integral, right? It's not too bad, right? It looks like it's simpler this way, okay? Which is exactly what they have over here, okay? Oh, actually, this one over here, okay? And if you do the result and you calculate, the result should be 36. Now, some people say, what happens if I do it this way? The first one, if I consider this as a type 1 region, what happens? If you consider that as a type 1 region, okay, so this one here, if you consider this as the type 2, okay, so this is type 2, like this, and then if you consider this as a type 1, like this, then you have to break it into 2 separate cases, okay? The first one here, you will have this y go from this to this. So y is going to go from, it's kind of small. Let me make it bigger for you. So the y over here go from negative square root of 2x plus 6, and then to positive square root of 2x plus 6. And then x go from -3 to -1. Okay. And then for this part over here, you have this y go from this one below, which is x minus 1. And then the above is square root of 2x plus 6. And then x go from here is -1 to 5. So you have to break it into 2. And looks like this one here is simpler. Okay. So if you have a choice, you can think about which one make it simpler. Okay, question here so far. Okay, more example. Okay, this is example number 4. So here is a tetrahedron. Okay, so what is a tetrahedron? This is an example of a tetrahedron. It have 4 surfaces. So 1, 2, 3 on the side and the bottom, the base. So 4 surfaces. Okay, and it's bounded by this plane x plus 2y plus z equal to 2. This plane over here. Okay, so let me make this plane over here a little bit distinguish that. I'm going to highlight it with yellow, and which is this one over here. This is the plane right here. Okay, can you guys see? Okay, so that's the plane. And then x equal to 2y, x equal to 2y is this one over here. Let's try the different color, okay? So x equal to 2y is this plane over here in front. Okay. Okay, this one here in front looks like there's a little bit, the purple one in front. Should I choose a different color? Okay, never mind. Okay, and x equal to 0. X equal to 0 is going to be x equal to 0. Imagine that one in the back. Okay, in the back of it. Okay, the one x equal to 0. Okay, that is this x equal to 0. X equal to 0 is this one here. X equal to 0 is the one in the back. Okay, it's the back wall right there. And then z equal to 0. Z equal to 0 will be the xy plane. Okay, so z equal to 0 will be the xy plane. So, the xy plane is z equal to 0. Okay, so you have this. Okay, now what are we trying to look for? We're trying to look for the value of this tetrahedron. Okay, so how do we do that? Can we think about the surface, this yellow one, the yellow surface here, right? It's going to project down to this xy plane here in a triangle, right? Okay, in this triangle. So we're basically trying to find the value of the solid that is under this surface and above this triangle on the xy plane, right? Okay, so that was the value. Okay, so under that. So we can try to think about this. From here, we should express the z here as a function of x and y, right? Okay, so from this, we'll have z as a function of x and y. And what does it equal to? We can just isolate z, right? Z is equal to what? 2 minus x minus 2y, right? And that's the function, right? That's the function you're going to integrate with, right? That's the function. And then over which region? Integrate this function over a region. And what's the region? The region is what? Down here on this xy plane, this triangle over here, right? And how does it look like? Well, let's just label those vertices of the triangle. So you have 0, 0 on the xy plane, this one and this one. So that's the region on this xy plane. Okay, you can see right here. Okay. And what was the function? So let's put it down. Z is 2 minus x minus 2y. Okay, that was the function you're trying to integrate with. Okay, now let's set up the integral. Okay, without looking at the book, let's see if we can do it ourselves. Okay, so the value of this tetrahedron is the double integral of this function. Okay, so that is 2 minus x minus 2y. Okay, Looking at this region over here, should we integrate with respect to x first or y first? What kind of region is this? Type 1 or type 2? 1. Yes, you got it. Okay, from here to here, right? So the y go from this to this, right? So this is the type 1 region. Okay, the y change from this to this. Okay, so now you're going to integrate with respect to y first. And y go from what to what? Y go from below to above, right? So that will be what? Yeah, 1/2 x. And then above will be what? Yeah, the above here is 1 minus x over 2. Okay, so it's 1 minus x over 2. Okay, so that's the y change through. And then let's now, after that, integrate with respect to x. Looking at this region, x go from what to what? X go from, am I going too fast? Okay, 0 to 1, right? X go from 0 to 1. Okay, 0 to 1. And you guys just set up the integral. And that double integral here represent the volume under the surface, So to do this type of problem and try to find a volume, you try to find the function for the surface, right? So you expect z as a function of x and y. So you isolate the z equal 2 minus x minus 2y. This is a function of x and y. And then you integrate this function over this region, over the shadow that it casts on this xy plane, and that will give you the volume of the solid over here. Okay, so that's how you set it up. And depends on what type that region is. You're going to, type 1, you integrate with respect to y first. Type 2, you integrate with respect to x first. Okay, all right. Now, after you set up this integral, the rest here just routine. Okay, you just try to find the antideuty, etc. Okay, and this is the most important part. Okay, do you guys want to take a break? Do you guys want to take a break? Okay, you guys don't want to take a break. Okay, continue. Okay, you don't see anything. Okay, so example 5. Okay, we try to evaluate the iterated integral. For double integral or triple integral, those are called iterated integral. So you integrate again and again. Okay, so this iterated integral over here, how do you evaluate this? Okay, well, if you evaluate this integral over here, sine of y squared, think about this. Think about this, sine of y squared. What's antideuty sine of y squared? Well, there's no elementary method to find antideuty sine y squared with respect to y, right? In 110b, also in other, we don't have a method to evaluate this antideuty sine y squared with respect to y. There's no such elementary function, okay? So what can we do? If you encounter some double integral like this, that the inner integral will be hard to evaluate, okay? Then you can consider change the order of integration, okay? How do we change the order of integration? Okay. This is the integral over a region, okay? So this one here is going to be not an elementary function, okay? So therefore, we want to do a change of order of integration, okay? But when we do that, we have to think about what is that region, okay? Let's think about what is that region. Can you tell me what is that region? What's that region D? You have to think about what that region here is in order to do the change of integration, right? So over here, what does it say? Let's see. Over here, it says that the y here is go from what to what? Y go from X to 1, isn't it? Right? Y is between X and 1. Do you agree? Okay, and what else we know? We know the X over here is, let me use a different color. The X over here is between what? 0 and 1. X is between 0 and 1, right? Okay, let's try to draw that region. So from this is actually two things. Okay, so the Y go from X to 1 is actually, the Y is above and below, right? Think about above and below. So the Y below is equal to X, right? Do you agree? The Y below. And the Y above is equal to what? The top, right? Is equal to 1. So you basically have the two curves, right? The top one is Y equal to 1, the bottom one is Y equal to X. And we know how to graph them, right? So Y equal to 1 is this one. Let me label this. Y equal to 1 is this one. This one here is on top. Let me see if I can. Right here. Okay. This one here is on top. Okay. And the one below is, choose a different color. This one here is below. This one here is below. Okay. This is on top. Okay. So you graph Y equal to 1 on top and Y equal to X below. But then keep in mind that X has a between 0 and 1. So X is between 0 and 1. So you're going to get this region over here. So it's going to be a triangle like this. Okay. So it's very crucial that you can draw the region, because when you do the change of the order integration, you have to have this region in mind. Okay. So this one here, when we consider this as the type 1 region, we have this integral. But this integral is really hard to, there's no, the inner integral is not an elementary function. So we cannot proceed using integration method that we have learned. Okay. Then we consider changing the order of integration. Okay. And then what do we do? Well, now we're going to consider this as a type 2 region. Okay, so let's consider that as a type 2 region. So what do we do? Now we're going to think about this. Okay. So what was the function that we tried to integrate with? So that was the integral that we're trying, and it doesn't work because we can't do this using those integration methods. Okay, and then now we're going to consider changing the order of integration. Reverse the order. Okay, let's do it. So when we do this, this is the type 1, like this. Now we're going to convert that into, because this region can be type 1 and type 2. So therefore, I'm going to convert that into a type 2 right here. So that's equal to, well, it's still the integral of the sine function, sine of y squared, but this time I'm going to reverse the order of integration. So I'm going to do dx first and then dy later. Okay. Let's think about what happened to dx then. Dx. As you can see, it goes like this, right? From here to here. So x go from what to what? 0 to y, right? Okay. And then y go from what to what? Yeah, y go from 0 to 1, right? 0 to 1. Okay. So, and then these two integrals are equal, okay? Because it's a same region, okay? It's a same region like that. Okay. So it's important you can think about what region it is. Okay, by looking at this, you can, okay, and the trick here is maybe make it easier is draw the arrow. Okay, this is the type 2 region. Okay. Okay, now when I do this, would this make the integral a little bit easier to evaluate? Now let's look at the inner one. Okay, so that will be what's anti-duality of sine of y squared with respect to x? It is because the y here considered as fixed, right? When you integrate with respect to x. So sine of y squared is considered as a constant. So we just have that constant. Think about that as a constant. And then multiply with x, right? Multiply with x. I don't want to put an x behind because it looks like sine, if I put like this, it looks like the y squared times x. So I don't want to do it this way. I want to put the x here in front. So then it's more clear that it's x times this quantity. Okay. And x go from what to what? 0 to 1, right? Okay. And now, after that, you integrate with respect to y. Y go from 0 to 1. Now it will be easier. Okay. So once you do this way, once you find that, you just substitute. Actually, I should put that maybe more specific. Which one you? Okay, I'm going to make it more specific. So it is x equal to y. This one here, x equal to y. Here, x equal to 0. So I know that I'm replacing this x here by y, and then replacing this x here by 0. Okay, so to be more specific. Okay, now when you do that, the rest over here just follow, and then this integral become much easier to evaluate, right? So this problem here just teach us that sometimes you can do a reverse the order of integration. If you can identify that region here as both type 1 and type 2, you can actually do the reverse of integration and just identify it. Okay? Question? Last section here. Property of double integral. Okay, this one is not too bad. Okay. So if you have, well, basically, what does it say? If you have the sum of this double integral of the sum, then what happens? It can be the sum of the double integral, right? Okay. So if you add this two, this is the sum law. Okay. And also with the difference law is the sum. Okay. And the second one here, it is a constant multiple law. So if you have a constant times this function, and if this integral, then you can take this constant in front. Okay, so this is the constant law. Okay, so there's a property. Okay, very similar. And the next one over here is this one over here. If this function over here, f is always greater than or equal to g, then the double integral of this function f over the region is always greater than or equal to the double integral g. If this is greater than or equal to that, this double integral is greater than or equal to this double integral, right? It makes sense, right? Okay. You can also prove it. The next property here is, it's kind of like this. Do you guys remember when we do integral from a to b? We can actually break it from a to c integral, and then another integral is from c to b, right? You can sum this up. Similar for double integral. If this region D can be broken into into D1 and D2, into these two regions, then the double integral function over this whole region is equal to the double integral over this region, adding the double integral over this region, right? Makes sense? Okay, what else we want to talk about? Oh, take a look here, okay? Look at this region. Is this a type 1 or type 2? Or neither? Just this. Look at the book. What kind of region? It's neither, right? It's not above and below. You see here? This above itself, right? So it's neither. So this is neither a type 1 nor a type 2. Okay. But how do we deal with this type of deal with an integral over this region? You can actually divide that. Okay, so what do we do? We're going to divide this. Okay, divide that. So then this region over here is what kind of region? D1, type 1 or type 2? When you draw the arrow, it is what? Yeah, it is a type 1, right? It's a type 1 region. And then what about this part here, D2? What kind of region? Type 1 or type 2? This one. Type 2. Yes, you got it. Okay. So this one here is type 2. Okay. So this is type 2. This part here is type 1. So sometimes you want to partition so then the region can be, each region is strictly type 1 or type 2, like that. Okay. And then you can integrate over. Okay, we're almost done. Okay. What happens when you integrate? Okay, think about this. Okay. What happened? The function here it is 1. The function you integrate here it is 1. And integrate that over a region, say D. See, G equal to 1. Okay, equal to 1 over here. So think about this height over here is always 1. And when you integrate this 1 over this region D, think about that as the volume, right? Isn't that the volume of this solid, right? Okay. So, hey. Okay. So this is 1. Can you see? No, cannot see. Okay. So this is 1, right? And then on this region here, D, then how do you get the volume? You use the base area times height, right? So the base area here is what? The base area here is the area of D, and then the height here is 1. But when you times 1, it's going to change the quantity. Times 1 is not going to change it, right? So times 1, you will get, so the result over here will be equal to the area of this base, okay? The area of this base over here, times 1, okay? So in number, that will be equal to the area of the space over here. But in unit, this will be cube, okay? This one here is square, okay? Right? So remember, when you do integration of the constant function 1 over a region, you actually just get the value of the solid that has height equal to 1 above the region, okay? Think about this is like the sponge, okay? Like that. And with height to be 1, the solid, the volume is equal to the base area times 1. Okay? Okay. Well, we can actually relate this. We can actually relate this to the one-dimensional case, right? So remember in one-dimensional case, you have this from A to B. What happens if the height here is 1? If a constant 1. What's the area for this? When we integrate 1 dx, x go from A to B. Okay. And what do you get? Yeah, you get B minus A, right? And isn't this the area? Isn't this the area? Isn't this the area under area of this, right? So that's the area over here. And now when we do integral of double integral 1, okay, of this dA. A here is this region D. That's equal to the volume that's above this region, and that's equal to this A of D, this area over here. Okay, and B minus A is actually, okay, in this case, B minus A is the length. It's also the length of this interval, right? Okay, so this one here is also equal to the area. So this volume over here equal to the area of the base, and this area over here, the area of this equal to the length of this. Okay, so that's how they relate. Okay, I feel like I'm trying to torture you guys. Okay, but anyway, we're almost done. Okay, so the last property over here is if this function here is bounded below by m, bounded above by m, then this double integral is going to be bounded below by m times the base area A, and bounded above by the big M times the base area AD. Okay, remember this one here. What is AD? This is the base area. Okay, base area. This is the base area. Okay, understand? For example, in this example, we know this function. Okay, suppose you try to estimate this integral. Okay, so what do we know about this? What do you know about sine x times cosine x? It is going to be between -1 and 1, right? Between -1 and 1. Sine and cosine bounded below by -1 and 1, right? Below and above by -1 and 1. Okay. Therefore, this, remember the exponential function is strictly increasing. So when you have, it's the exponent here is bounded below by -1, bounded above by 1. Then this is bounded below by e to the -1 and e to the 1. Okay, and therefore by that last property that we have, this double integral is going to be bounded by e to the -1 times the base area. How did they get this base area over here? Okay, the base area over here, they gave you D is a disk with center to the origin and radius 1. So that D is a disk for this. So the area of this disk is going to be pi times 2 square, so which is going to be 4 pi. So you will have 4 pi times e to the -1, and then this one here is 4 pi times e. Okay. All right, we finished with 10.2.